Welcome to the next video of Machine Learning Techniques course. In this video, we'll discuss a couple of components of linear regression model. First, let's discuss about the model of linear regression. As you know, linear regression computes the label y as a linear combination of features. And there are m features in general, x1, x2 all the way up to xm. So the label y as a linear combination can be written mathematically as y is equal to w0 plus w1 x1 plus w2 x2 all the way up to wm xm. Here w0, w1, w2 all the way up to wm are called as weights. And you can notice that each feature xj in general has a corresponding weight wj. For example, x1 has a weight w1, x2 has a weight w2, x3 will have a weight w3, and in general xj has a weight wj. Okay, so there is only one exception at the beginning where this particular weight w0 does not have an associated feature. So what we do is, in order to have a uniform representation, we add a dummy feature x0 and set it to 1. So after doing that, we get a new form, which is, we get the same form with x0 added to it, right? So y is equal to w0 x0. Remember, this x0 is 1, so it is not a different equation than what we have written over here. So w0 x0 plus w1 x1 all the way up to wm xm. This particular arrangement helps us in writing the model in a compact form as a sum over all m features. So y is equal to sum over all m features wi xi. So it's a linear combination of features, right? So this is how we can compactly represent the model, and you will see that this compact representation will help us in vectorizing this particular computation for efficiency purposes. You may be wondering, what does this model corresponds to, or how does this model look like? For that, we take a simple model with a single feature x1. Whenever we take a single feature, it becomes easier for us to visualize that model. So our model becomes y is equal to w0 plus w1 x1. It has got two features, or it has got a single feature x1, and it has got two model weights, that is w0 and w1. So the equation of the model is y is equal to w0 plus w1 x1. This is the model. So does this ring a bell? Can you actually recall what does this equation look like? What geometric figure does this equation represent? Yeah, you may recall from your college days, you may recall from your school days that this resembles to equation of the line, which is y is equal to mx plus c, right? So where m corresponds to w1 and c corresponds to w0. Yeah, indeed, it's a case. So we can, and another thing here is that since these are the model parameters, right, we do not know them explicitly. We do not know the values of w0 and w1, and in fact, one of our job is to obtain these values, right, through the training procedure, right? So right now, in order to understand how this model looks like, what we'll do is we will try different combinations of w0 and w1, and we'll plot different models, right? So each combination of w0 and w1 gets us a new model. So let's plot a few models for illustration. So here we have actually plotted 4 different models just for the purpose of illustration, and you can see that the first model, which is represented with a red line, which is over here, has equation y is equal to 0 plus 0.5 times x1. So you can see that w0 is equal to 0 and w1 is equal to 0.5. So the slope of the line is 0.5 and the y-intercept is 0, right? So you can see that this is the red line. And then we have another line, which is this green line, which differs from the red line only in its intercept, or the value of w0, right? So the model for the green line is y is equal to 0.5 plus 0.5 times x1. Right, so you can see that this particular red line and green line, they are parallel to each other. They only differ in the intercept, but the slopes are the same, right? The slopes are the same, or the value of w1 is the same, and that's why they are parallel lines, right? They are parallel to each other. Now we have another model where we change the value of w0 to 1 and w1 also to 1, so we get a line at 45 degrees, right? And then we have one more example, which is this blue line, which has got w0 of 0.3 and w1 of 0.1. So the equation or the model is y is equal to 0.3 plus 0.1 times x1. So you can see the blue line over here corresponding to this particular model, right? So how many such kind of models are possible? Remember, we can use, because w0 and w1 are basically real numbers, we can try infinite number of real numbers here, right, as possibilities, as a possible value of w0 and w1. So this leads to literally infinite combinations, right? So total number of possible models are infinite, and our job is to find out the model that fits our training data well, and that's what we are trying to do to the training procedure. Okay. So you may be wondering, it is fine for single feature that we have a line as a model. In general, the geometry and the number of parameters of the model depends on number of features, right? So for a single feature, we already saw that we have a model that corresponds to line in geometrical sense. The model is y is equal to w0 plus w1 x1, which indeed is the equation of the line, and it has got two parameters, w0 and w1, which you can see in red. These are the parameters of the models that are not known, and we are supposed to learn them through the training procedure. When we have a number of features equal to 2, we have the corresponding model y is equal to w0 plus w1 x1 plus w2 x2. There are exactly two features, x1 and x2. This represents equation of plane, right? So this model corresponds to plane in geometrical sense, and it has got number of parameters equal to 3. So in general, right, so this should actually be greater than or equal to 3. If you have number of features greater than or equal to 3, we have a model which is a linear combination of m features, or rather m plus 1 features, where we have added a dummy feature x0 at the beginning corresponding to w0. So we have a linear combination model. These are also linear combination models, but we have expanded them and written them in order to make them explicit, right? So that you can see the geometrical equation in this, right? So this represents the equation of hyperplane in m plus 1 dimensional space, and this particular hyperplane has exactly m plus 1 parameters, or in other words, number of weights is equal to m plus 1. So there are m weights corresponding to m features and one more weight corresponding to the bias. Okay. So in order to perform efficient computations, as we studied in the previous module, we generally tend to write our models in a vectorized form, or we tend to perform different computation in machine learning in vectorized form. So our model, which is a linear combination of the features, it can be written compactly as a product of two vectors, right? The weight vector and the feature vector. So we can write it as W transpose X. We'll verify whether this W transpose X is indeed equivalent to the linear combination. So we'll try to perform the multiplication of these vectors and verify that it indeed corresponds to the linear combination of features. So we have m weights and one more weight which is corresponding to the bias unit. So we have in all m plus 1 weights. So we can arrange it in a vector w with shape m plus 1 cross 1. And we have a feature vector corresponding to ith example containing m features, and we add a special feature x0 and set it to 1. So the feature vector also has a shape of m plus 1 cross 1. And now we have to perform multiplication of these vectors in order to obtain the label for this ith example. So what we do is we write down the vector corresponding to the weight. So this is a weight vector into the feature vector. And recall, by definition, a vector is a column vector, right? So here you can see that if we just try to multiply these two vectors, we do not have the shape compatibility. So in order to get the shape compatibility, we take the transpose of the weight vector and then multiply it with the feature vector. So when we take a transpose of the weight vector, we get basically a row vector with shape 1 cross m plus 1, and this has got shape of m plus 1 cross 1. So we get a shape compatibility, and now we can multiply these two vectors. So let's multiply these two vectors. So when you multiply it using the rules of vector products or matrix product, you can see that W0 gets multiplied with 1. We add the multiplication between W1 and X1 all the way up to Wm and Xm. And now you can see that, and we actually replace this 1 with X0, right? And now you can see that this is indeed is equivalent to the linear combination of the features. Okay, so we actually did this derivation explicitly. I know many of you will have background in doing this, but we thought we will do this explicitly so that you get used to the vector notations, and you can indeed verify this vector notation is equivalent to the linear combination. Right? So I would urge, whenever you see such kind of equations in the machine learning course, try to derive them from scratch. It will help your understanding a great deal. So now we saw how to obtain the label for a single example. Right? We can take a vector product which is W transpose X. We get label for a single example. So we can also find out, we can also have a vectorized implementation where we can obtain labels for multiple examples all at once using the matrix vector multiplication. So let's see how to do that, right? So we have a weight vector W with shape m plus 1 cross 1. So this is our weight vector having m plus 1 weights starting from W0, W1 all the way up to Wm. So these are weights corresponding to m features, and we have additional weight corresponding to a bias unit. And we have a feature matrix X with shape n cross m plus 1. So we have one additional feature which is corresponding to the spatial or dummy feature that we added and set it to 1. So that's why the feature matrix has a shape n comma m plus 1. So it has got n examples and m plus 1 features. And again, remember that the feature vectors for each example are transposed and are present on the row. Got it? Now what we'll do is we'll obtain the label vector y containing labels for all n example at once by computing multiplication between the feature matrix and the weight vector. So here we have written the shapes of the matrix for your reference. So X is equal to X has shape of n cross m plus 1, and W has a shape of m plus 1 cross 1. So you can see that they have compatibility of shape, so we can perform this multiplication, and this will result into a label vector with shape n cross 1. So by doing this particular vectorized operation, we obtain labels for all example at once. So this is a very useful useful trick to know, right? You can use this to obtain labels for all examples at once. So let's implement the vectorized form of the model inference. So we can use x times w, the vector matrix, the matrix vector product, to obtain labels for all n examples at once. So we can represent this, we can implement this in a vectorized form with a Python function. The function name is predict. It takes two arguments. The first is the feature matrix and second is the weight vector. We check the shape compatibility and then we perform the matrix vector multiplication to obtain y, and finally we return y, right? So this is a simple representation, or this is a very simple implementation of the predict function or the model inference. And because we have this vectorized form, our code becomes cleaner and also efficient in terms of computing the label vector corresponding to all the examples, right? So the label vector will have labels for all n examples in the feature matrix. Now that you know about how model looks like and how to perform model inference, let's go to the next question about choosing the best fit model. Let's explore this question with a simple model with a single variable or with a single feature. So our model is y is equal to w0 plus w1 x1. Note that there are two weights w0 and w1, and there is a single feature which is x1, and of course y is the label. And you know that as we vary the values of w0 and w1, we get a new model. And we have already seen this illustration where we simply change the values of w0 and w1 and we got different models. Now the question is, which of these models fits our data better than all other models? So we want the model that fits our data better than all other models. So what we do is we also plot data in the same figure where we had earlier plotted different models. And now you can see that this particular model with a purple color, right? This purple line seems to be fitting data better than all other models or all other lines. So how do you exactly evaluate this model fitment? So for that, we possibly need a measure of fitment or misfitment. So something like this, right? So let's say we have a model which is represented by this particular blue line, and these green circles corresponds to actual points in the training set where they have feature x1, and for the corresponding feature x1 we have a value of y. And this is the actual value of y in the training set, and because we had a model which is this blue line, because of this particular model we actually obtain the value for this particular x0, we get this particular value of y. So here there is an error that we incur because of this prediction. And you can see that for different points there are different amount of errors that we incur because we chose this particular model. And these errors can be easily computed based on the difference between the actual value of y and the predicted value of y, which is the predicted value is on the on this particular line or on this particular model. So you can see that for this particular point there is higher error compared to, let's say, this particular point or this particular point. So this particular point is very close to the actual point, right? So the predicted value and the actual values are very close over here. So you can see that there are the error incurred due to model varies greatly from one training point to the other, and we need to accumulate, or we need to sum up all these errors and across all the training point, and that will probably give us a measure of fitment or a misfitment. And this measure is formally known as loss or error function, which we will be discussing in the next video. Hope you have a better idea about the linear regression model and what does it geometrically corresponds to. Now you also know how to come up with a vectorized implementation of it, and and also you have some idea about how to, intuitive idea of course, about measuring the fitment of the model. So let's discuss loss function in the next video. Namaste.